Hey guys, alright, so over here I'll be quickly going over the code for my sentimental analysis project. So the problem we're trying to tackle is that given a tweet, we want to predict whether the person writing the tweet wrote it with a positive attitude or whether he wrote it with a negative attitude. So the database we are going to be using is the database over here on Kaggle. It has over 1 million tweets. And as you can see, the first column over here represents the sentiment of the tweet. So the zeros over here represent a negative sentiment. So that could be something like sadness or anger. And the 4 over here represents a positive sentiment. So that could be something like happiness or joy. Now, if you look at the last column of our database, it contains the text that the users have tweeted. And that's almost pretty much the information that we'll be using. All right, so now that we have gotten a sense of the structure of our dataset, let's dive right in. Okay, so first off, let's just discuss all the packages that we'll be using in this project. Matplotlib, Seaborn, Pandas, and NumPy would help us visualize and better organize our data. Next package, NLTK, would help us clean our data. Now, what are the steps that generally go into cleaning our data? We'll just look into those steps momentarily. After our data is cleaned, we are going to use the scikit-learn package to pre-process our data. Once the data is pre-processed, we can finally use TensorFlow to create a recurrent neural network model. Okay, so our very first step would be to actually extract the data that we need from the Kaggle database. So over here, I'm using pandas to extract the first and last columns in the database. We are not going to be using all the 1.6 million data points. Instead, over here, all I'm doing is I'm extracting only 100,000 random data points from our data set. After that is done, this is how our data set looks like. In many of these tweets, we have at mentions, or we have some sort of spelling errors, or we sometimes might even have words which the computer might only see once or twice and never see again. So the very first task that we want to do before we train our model, is to actually clean up the data. So the first thing that we can do is remove any kind of hyperlinks, remove any kind of at mentions, and remove any kind of hashtag mentions that we see. Once we do this, this is what the data looks like. Now, before we move further with the cleaning, what we need to do is we need to tokenize our tweets. Tokenizing is a process that would convert our tweets into an arrays of words. Now, we do this so that it would become easier for us to iterate through the whole array and then remove any words that we feel are unnecessary for training. So for instance, after we have tokenized our tweets, we could remove any stop words that we see. Now, stop words are words in the English dictionary which don't really add any meaning to the sentence, but are still there to give the sentence some kind of grammatical structure or meaning. So for instance, words such as don't, can't, shouldn't, um, the, and, these words don't really add any meaning to the sentence, and we can remove these words from our model. Now that we are done removing all the stop words, our next process is to stem each word. Now, stemming is a process that helps our model recognize that words and its conjugates are the same words. So, for instance, words such as drinking, drank, drunk would all turn into its stem word drink. Words such as happiness and happy would turn into its stem word happy, which ends in an I. And then stemming also helps our model recognize that a word and its plural are the same words. So, for instance, updates would turn into update. It might seem a little weird the way how this process of stemming works, but it's a huge step in most NLP projects and gives fantastic results. All right, we have finally reached the pre-processing step in our model. So first off, we have to recognize that an RNN model cannot really intake an array of words. Rather, we have to convert each of our tweets into a equal length vector of real numbers. So one of the most common ways to do this is to convert the tweets to create a frequency list. Now, this is the code over here for creating a frequency list. And what this essentially does is that it tells us, for instance, the word drink in a positive connotation, in a positive sentiment, appears 279 times. The word juice in a positive connotation appears only 35 times. So doing this and then encoding these words with the number of times they appear in our training data set essentially tells the model how important each word is. So it tells the model that for a positive sentiment, the word drink is really important, but a word something similar to juice is not that important. Now, I want you to notice how the length of our word frequency list is actually 45,000 words. So that's a huge vocabulary list for our model to train on. What might be some of the reasons that we have such a large list of words? Well, remember how at the start of the video I said that the tweets might have some misspellings or certain slang words that perhaps we only see once or twice in like 100,000 tweets. Now, these words aren't really going to help our model train better. So we should try to remove any words with frequency of 3 or less that we see. And once we do this, we actually see the words drop from 45,000 all the way down to 10,000. Much better. Okay, so we are finally ready to encode all of our tweets. But notice how the length of each tweet is different. So that would imply that the length of all of our encoded vectors is also different. But for an RNN model to work, we need equal length real valued vectors. So one of the things that we could do is we could pad every vector with a bunch of zeros right before it. So the code over here does that, and it results in a vector that looks something like this. But now notice how before our encoded vector, we have a 1. Now, this is true for every single vector. The 1 essentially tells our model that, look, all the data before the 1 is irrelevant, ignore that, and concentrate on the information right after the 1. All right, so we are finally ready to train our model. The type of RNN model that we'll be using over here is called an LSTM model. It stands for Long Short-Term Memory Model. And essentially, the LSTM models are really good with long sequential data. So sequential data is a type of data where the prior term heavily influences the term that comes right after it. So LSTM models are really good with these, and we're going to be using them. Our first step would be to simply create a model, initialize a model, and then what we're going to do before we add the LSTM model or the LSTM layer is we're going to add an embedding layer. Now, in many NLP projects, the sentences that are being used are actually quite long, and the encoding that we can do, especially if the person uses hot encoding, might actually lead to a vector that has 500 to 1,000 letters in it. So over here we only have 209, but I'm still going to add an embedding layer because, after trial and error, I saw that, adding an embedding layer which converts our 209 length vector to a 200 length vector still improves the efficiency of our model on the validation data set by almost 2%. So I'm still adding the embedding layer over here. After we are done adding the embedding layer, we can finally add our LSTM layer. After we're done adding the LSTM layer, we're going to add another hidden layer, and this is a dense hidden layer. So every single node in this layer is connected to the last, to every single node in the last layer of our LSTM model. And then finally, we can add our output layer, which only has one node since we only need a binary return value, either a 1 or a 0. Now that we're done creating the model, say you want to try a different model and you want to change the internal values, what you could have is you could have another section right on top of your LSTM model, and call it hyperparameters. And basically, you could change all the values over here. So you could have an embedding dimension over here. You could also change the LSTM, the number of nodes in your LSTM model or your hidden network, or even the epochs or the learning rate. And a neat trick that I like to have is that you could have another for loop, and you could have a list of hyperparameters and then run the for loop on all the hyperparameters and have results for on like 20 or 30 models all in one go. All right, now that all of that is done, we are finally ready to train our model, and let's have a look at the results. So the results are looking pretty good. As you can see over here, I have created a visual representation of the training loss reducing over a span of 5 epochs. And then after that, I wanted to compare it with another model. I wanted to compare it with the binary cross entropy model. And we essentially use this model for any binary problems, such as the one we have where we are classifying the tweets into either a positive category or a negative category. And if you see, the performance of the binary cross entropy model for the training set was only 40%, and for the validation set was 50%. And if you think about it, since we only have two outputs, and the validation accuracy is 50%, the model is basically just guessing. So let's see how it performed with our RNN model. So if you want, you can create two confusion matrices to compare our results for our RNN model with the results for our binary cross-entropy model. So if you look over here, the accuracy for the training data set for the RNN model was 82%, and the accuracy on the validation model was 76%, which is already much better. Hey guys, the video was a quick overview of my code. If you want to gain a deeper understanding of some of the concepts that I went quickly over, like embedding layers or how RNN models work, or see the performance of this model compared with other models, check out the link in the description below. Thank you so much for watching.